Okay, it's time to get started because we have a lot to cover today. I always get a bit too over-enthusiastic about this lecture because it's so fun and there's so much really exciting stuff to say. So today we're going to be talking about Earth's place in the solar system. And you may have gathered by now that I'm not really interested in just reciting sections of the textbook at you. You can do that yourself. You should be reading the textbook as we go, and it's really boring if I just tell you the same stuff that's in there. Instead, I want to try and bring in some of the bigger questions that sort of Earth system science is trying to address right now. And in particular, the question that we're really interested in when we talk about exploring our solar system is there life anywhere else in the solar system? Is there life elsewhere? And so I asked you to do the reading associated with the textbook. It should be stuff that you've known from school, things like how many planets there are, that we have moons, things like that. And so instead today we're going to skim through that quite quickly. If you don't know anything, then do make the effort to go and read it in the book. And then we're going to spend a lot of today actually talking about what is necessary for life, what makes Earth such an amazing place for life to have sort of formed and developed. And could there be life elsewhere? Which is a really fascinating question. Okay, so who knows what this is? Yes, this is Mars Curiosity, which is busy exploring Mars right now. Even with the government shutdown, it's still rolling on. And so it's one of the really interesting times when we're finding out a lot about the different parts of the solar system. Okay. So, as a quick outline, we're going to give you a very brief, like 10-minute introduction to the universe and everything. And then we're going to think about what's necessary for life, and then go on to talk about potential places within our solar system, and then sort of even further out, potential places outside our solar system. So, some real basics, because I know some of you haven't set foot in a science class for a very long time, okay? So this is we want to introduce the idea of atoms and elements, and this should be, again, a review from what you've learned at school. But remember that the most basic sort of building block of matter is the atom, okay? And atoms are made up of protons and neutrons, and those both have a mass unit of 1, and they make up the nucleus of our atom, okay? And protons have a positive charge, and neutrons are neutral. It's a nice, easy way of remembering it. And then orbiting that nucleus in different energy levels, we have electrons. And those electrons are so light that we just sort of ignore their mass, but they do have a negative charge. And then we look at elements. And elements are the simplest unit that you have that you can't break down any further in sort of chemically. So if you have carbon, a lump of carbon, you can't break it apart into two different things. It is an element. And elements are really defined by the number of protons in the nucleus. If you have 6 protons in your nucleus, you are carbon. It doesn't matter if you have a couple of extra neutrons or a couple of less neutrons, you're still carbon, okay? And then it's the electrons sort of circling around that control the chemistry that goes on. Okay, so this is what atoms and elements, and this is figure 3.4 from your textbook. If this isn't sounding familiar, or if this was just way too long ago that you were looking at this, then do go back and have a look in your textbook. Okay, and this is something that looks very familiar to everyone, the periodic table of elements, where we've organized the different elements into different groups, and you can see that the number of protons, what we call the atomic number of the element, is increasing from the top. So hydrogen has 1 proton in its nucleus. It's always hydrogen. Helium has 2. Lithium has 3. Beryllium has 4, etc., etc. Okay? And that isn't taking into account neutrons. So in fact, if you look at carbon, carbon has 6 protons in its nucleus. It also has 6 neutrons, so it has a mass of 12. Okay, and we'll come back to this in a minute because we're going to talk a lot today about elements. The other thing I wanted to reintroduce to you, and again it's something that should have been done at school, is gravity. So gravity is a force, and compared to other forces, it's pretty weak. But it does occur over very large distances, and especially for the universe, it's been very important in sort of pulling together matter to create solar systems, to create galaxies and nebula and things like that. And so you can see this is the formula here. So the force due to gravity is equal to the gravitational constant. So constant doesn't change. And then it's related to the mass of the two bodies divided by the distance between them squared. Okay? So even really small particles of dust can feel a slight gravitational attraction, and over a very long time, that can sort of bring things together. So it's a very important force for the universe. Okay, so the history of the universe in about 30 seconds. There was the Big Bang. Okay, that was about 13.7 billion years ago, as far as we can tell, if we look at the expansion rate of the universe and sort of play it in reverse. Okay, and during that first instant after the Big Bang, there was the temperature was so high that really only energy was present. There was no matter at that point. But within the first 5 minutes or so, we'd started developing those elements. We'd started creating hydrogen, and 98% of the matter that was produced at this time was hydrogen. We had small amounts of helium, maybe 2%, and then trace amounts of lithium, beryllium, boron. So remember, if you remember back to the periodic table, those are the 5 lightest elements we have. And those were the elements created by the Big Bang. And over time, so when I put MA there, this is something that geologists do a lot. I mean millions of years. So A stands for annum, which is years. Okay? So after 200 million years or so, all of that hydrogen and helium had started forming clouds. And we call one of those clouds a nebula, and the plural is nebulae. And you might see beautiful Hubble images of nebulae around. By 400 million years after the Big Bang, so no time at all really, gravitational attraction had caused parts of that nebula, or different parts of the nebula, to come together and become denser and denser, and all of that material started packing closer and closer together. It got hotter and hotter and denser until we actually generated enough heat and pressure to ignite the first stars. We created the conditions suitable for nuclear fusion to happen, and those were our first stars 400 million years or so, we think, after the Big Bang. Okay? And really, it's that nuclear fusion within stars and subsequent supernova, with those stars exploding, that has created all the other elements that we see. The Big Bang only really created those 5 elements, and really most of it was hydrogen and helium. So if you look at your hand and think about this, the hydrogen in the water making up your hand was created during the Big Bang. The carbon in your cells, the other elements making up the proteins and carbohydrates like the oxygen, everything else, was created within a star. And I think that's really cool. So you've all heard that, the songs and everything, we are stardust. We really are, okay? We're made up of elements that were fused together within stars, and I think that's so cool. And subsequent to these sort of stars, we've developed sort of more organized patterns of galaxies, of sort of clusters of billions and billions of stars. We've started developing planets around these stars, and the expansion of the universe is continuing. So there you go, history of the universe in 30 seconds. So I wanted to talk a little bit more about nuclear fusion. It's important for a couple of reasons. So first of all, because we need to generate those heavier elements. So if you think about what's happening in our star today, our star is mostly hydrogen with a little bit of helium thrown in as well. And in the core of our sun, in the core of that star, hydrogen is fusing together to form helium. Okay, so we take 4 hydrogen atoms and we create 1 helium atom from that. Okay, but what happens when our sun runs out of hydrogen? What are we going to do? What's going to be left over? What are we creating? We're creating helium, so what could we fuse next? Helium, okay? So once our sun runs out of hydrogen, we're going to start fusing helium. And when we fuse helium, we can start creating heavier and heavier elements. And the highest or the heaviest element that we can really create in a star like this is iron. Iron has a mass or a atomic number of 56, and it really we can't get much higher than that, okay? And then if you think about the pressures and temperatures involved in supernova, so when stars explode, that's how we've created even heavier elements like gold, platinum, uranium, things like that. The really heavy elements, they were produced in supernova. Okay? There's a little YouTube video there if you want to find out a little bit more. Okay? So, because everyone seems a little bit asleep today, how many helium atoms would I need to fuse together in the center of a star to form a carbon atom? So I've even put the periodic table there. So look at how many protons helium has, how many protons carbon has. Should be a nice, easy first question of the day. A few more seconds. Okay, let's see how awake people are today. Oh, good, pretty awake. Okay, so if we look at helium, helium has 2 protons, has a mass of 4, and we want to create a carbon atom which has 6 protons and a mass of 12. So how many 2s do we need to get 6? 3, okay? So we would need to fuse together 3 helium atoms to produce a carbon atom, okay? So nothing too complicated there. I think the people that put 6 perhaps thought they were fusing together hydrogen. And if you're fusing together hydrogen, you might need to fuse together 6 to get that, okay? And of course, this is a massive oversimplification. The actual process that does this is a little bit more complicated, but you get the idea that this is how we build up the heavier elements that we need, okay? So we've built our galaxy and we had our Big Bang, but let's think more in detail about our solar system. And we can get an idea about how our solar system formed by looking out around at other suns and other stars in different parts of our galaxy and looking at the different stages of the sort of formation of these solar systems. And we think this is what happened. We were once just this sort of big cloud of dust and gas floating around in space left over from previous supernova that happened, previous supernovae. And it was ever so slightly gently rotating. And over a very long time scale, hundreds of millions of years, gravity pulled together those sort of dust and those gas particles, and the center of that cloud started getting denser and denser and denser and denser, and gravity sort of pulls it together. And as those particles move in towards the center, they take that kinetic energy, that energy of their movement, and as it sort of collides in the center, it releases that kinetic energy, it transfers it into heat. So the center of this sort of cloud gets much, much denser and it gets a lot hotter, and eventually we hit that point where nuclear fusion can begin, where we've created enough heat and pressure, okay? And we think that sort of fusion of our sun, nuclear fusion in our star, was born about 5 billion years ago, okay? And then we still had a big sort of flattened out disk of dust and gases around that central star. And those are the materials that sort of what we call accreted, that came together, again due to gravity, to form the planets and everything else that we see in our solar system today. And we'll see that there's a pattern again to where the planets are and what they look like, related to the way that this material was distributed in that sort of disk of material around the star. Okay, so the solar system, you all know this. I'm not telling you anything new. There is one sun, there are 8 planets. Because we had to chop poor Pluto off the end, it no longer is a planet. We have a huge, vast number of asteroids, especially between Mars and Jupiter. It's almost like a failed planet really there. And we have this asteroid belt. We have millions and millions of comets and lots of moons. We only have one, other planets have a few more. And asteroids, planets, comets, they all orbit around the sun. Moons are the things that will orbit around the planets. Okay. And they all have pretty smooth, regular orbits sort of defined by the gravitational attractions that they feel. They also rotate. Does anyone know the only planet in our solar system which rotates the other way to all the others? Venus, absolutely. Venus is the only one that rotates the other way. Okay, and we'll come back to that in a second. But the early solar system was a really violent place. We think of this stuff gradually coming together, but as sort of particles became larger and larger and larger, then you can imagine that those collisions started becoming really very large. And so one of the things that I'll come on to later very briefly is that our moon, has anyone ever wondered why we have a moon? Where did it come from? We didn't capture it. Actually, something the size of Mars collided with us pretty early on, maybe about 4.5 billion years ago, and it basically remelted a huge amount of the Earth, and it was sort of slightly off-center impact, so it started us spinning, gives us our 24-hour days. It also made our axis tilted. So the moon formation was an important thing for the Earth, and it's helped keep us a little bit more stable ever since. It stops our axis wobbling too far backwards and forwards. Okay. And I wanted to mention comets again briefly because who knows what is happening in the next month or so? We're getting visited by something. Has anyone heard of Comet ISON? No? Does no one ever read the news? Okay. We have Comet ISON, and this was discovered last year. It's its first trip into the solar system. It's probably its last. It's on a sort of exit velocity. Okay, and this is it. And it's going to probably come past us in the next few weeks, and then it's going to go really, really quite close to the sun. And by close, I mean 700,000 kilometers or miles or something. But that's really very close for the solar system. And we don't really know what's going to happen. Last year, we were really excited. We thought this might even be visible during the day at times. It's probably never going to get that bright, but it should still potentially be bright enough that we could see it with your naked eye if you go outside. And definitely, if you own binoculars, you could go outside in the next sort of month or two and hopefully be able to see this. So I'll post something to the Facebook group about how you could do that. But this is fun. I wanted to show you a quick video of where it's sort of coming from. So this is produced by NASA. And you can see the comet ISON coming into our solar system, and it's going to shoot past Mars. And this is what happened last night. It shot past Mars, and they used the rovers and the orbiting satellites to take pictures. And then it's going to come in, and on Thanksgiving Day, it's going to loop around the sun, and then it's going to head out again. And look, the tail is always pointing away from the sun. Everyone thinks of comets as sort of coming around and shooting out. The tail always points away from the sun, okay? So don't let that confuse you. So this is the comet ISON, and it's really fun, so do keep an eye out for stuff in the news and the media about that. Okay. So let's just think about the planets. So the planets are the big things. If we're going to think about potentially finding other sort of suitable planets, we want to think about what types they are. And we have two types of solar system. We have two types of planets in our solar system. We have terrestrial planets. So like they sound, they're smaller, they're rockier, they're denser, and they're close to the sun. So Mercury, Venus, Earth, and Mars. And then we have what we call the Jovian planets. And these are our gas giants. These are Jupiter, Saturn, Uranus, and Neptune. And then Pluto got demoted. Okay? And the reason that we have these differences in composition is due to that formation of our initial solar system. So if you imagine when the sun was started burning, it's warmer towards the middle of the solar system. And so things like the gases, the hydrogen, the helium, water, ammonia, things like that, couldn't condense out to form planets. Those things actually had to condense further out in the solar system. And so instead, what we ended up being made up of closer in is the stuff with the sort of the much higher condensation temperature, or the higher melting point. So things like sort of silicon, oxygen compounds, things that are sort of more rocky in nature. Okay. So let's have a look at what these look like inside. So I've switched this around a bit. So let's look at terrestrial planets first. So these are just rocky bodies, and those sort of formed from collisions of all that sort of rocky material that condensed out around the inner part of the solar system. And again, as those sort of larger collisions started happening, as we built up bigger and bigger and bigger rocky bodies, then the heat released in those impacts started melting some of the rock. Not only that, but these bodies also contained radioactive material. And as those radioactive elements decay away in the center, they release heat. And that heat is trapped in the center, and it goes into melting some of the material. And as you know, when stuff melts, heavier stuff will sink and lighter stuff will rise. And basically that's what happened with our terrestrial planets. The heavy stuff, like the iron, the nickel, the metals that form our core, sank down to the middle, and the lighter stuff, the stuff that makes up our crust today, rose to the top. And this is a process called differentiation. It's this formation of different layers that we're all familiar with now. And it's nothing unique to the Earth. All of the terrestrial planets differentiated, they all formed these layers. And it's not even unique to planets. Some of the moons did this. Anything large enough can do this. And a lot of the meteorites you get, if you've ever been to museums and you see meteorites and they're completely made of iron or something like that, that's because they were from a body that differentiated. And actually what you're looking at when you look at some sort of meteorite that's made of solid iron is a bit of that sort of that body's core. And that's a good sort of piece of evidence for us about what the different layers are all composed of. It's really fun stuff. Anyway, so what part of Earth generates our magnetic field? Because our magnetic field is actually pretty important for life. So as a quick sort of assessment of how much you remember from school, because I know it was a long time ago for most people. Is it the crust, that outer skin? Is it the mantle, the stuff underneath the crust, or is it the core, either the liquid outer core or the solid inner core? Last couple of seconds. Okay. Oh, I caught you. So it's 1-1 so far. Okay. So it's actually not the inner core that generates our magnetic field. It's actually the liquid outer core. Okay? It's the movement. It's the movement of that ion that generates a magnetic field. Okay? So if you got C, you're a minority, but you are correct. So well done. Okay. And we'll come back more to this next week when we talk about structure of the Earth and things like that. Okay. So why did I ask you that question? Because it's something that we associate our magnetic field with our metal core. But actually, if we look at the Jovian planets, really weird stuff goes on because of the pressures involved, which is really fun. So we think, it's difficult for us to tell for certain because these things are so dense, but we think that Saturn and Jupiter at least have rocky cores. So just like the terrestrial planets like us, they have rocky cores, probably even bigger than us. But the difference is that they have a lot more gas, and their mass has allowed them to retain that hydrogen, to retain that helium, because they're so enormous. And because they're so huge, around that central core of rock and ice, then that hydrogen is so compressed that it turns into liquid, and it even sort of becomes metallic in nature. The electrons don't get as tightly tied to the protons. And so it actually sort of becomes like a metal. And these planets also have some aspects, some parts of a magnetic field, and it's generated by this liquid hydrogen, this metallic hydrogen, rather than by iron. And I think that's also fascinating. So much cool stuff. Okay, so that's really the introduction. That's the basics about the solar system and the Big Bang and galaxies that I'd like you to know about. But what we're interested in, especially in Earth science today, is what's necessary for life, where could we find it? So this is my question for you. So talk to your neighbors for a couple of minutes. See if you can think about the things that life really couldn't exist without. And I came up with 4 things. So see if you can come up with at least a couple. Okay. Does anyone have a suggestion for me? We had lots of good ideas on this side of the room. So how about over here? Does anyone want to give me one thing that you think is important for life? I heard it, water, absolutely. Liquid water is a really good one. And I know I say it funny, but I can't say it your way, water. So liquid water is one way of doing it. And how do we develop liquid water? What do we need for water to exist in its liquid form? The sun. The sun. We need some sort of energy, right? Okay? So whatever form, we need energy. Anyone else? Why am I focused on elements so much? Yeah, we need carbon, we need nitrogen, we need oxygen, we need the fundamental stuff that life can form from. So we couldn't have had life as we know it in some of the earliest sort of solar systems and earlier stars because there wasn't enough carbon, oxygen, nitrogen, things like that floating around for us to exist, okay? And I think that's really the main ones that I was getting at. So they're really fundamental, but it's a good place for us to start thinking about it. So these were my 4. So first of all, we need the elements that we need for metabolism, reproduction, things like that. And so the big 6 are carbon, nitrogen, sulfur, phosphorus, oxygen, and hydrogen, but that's always around, okay? Secondly, and I've underlined it because even if we have everything else, without a source of energy, we are not going to have any life. That source of energy is really by far the most important one. And it's also tied in to the others. It's tied into the presence of liquid water. So again, for life as we know it to exist, most of the reactions that happen on Earth that are biological are mediated by water in some way. And so presence of liquid water is important, and we need an energy source in order to have that liquid water around. And then lastly, I've lumped in a whole bunch of stuff, which you probably came up with, which is things like the presence of an atmosphere, protection from radiation, so things like the ozone layer on Earth helps us. The presence of a magnetic field protects us from certain radiations, and it also protects our atmosphere from being blasted away by the solar wind. And things like environmental stability is an important one. We've had a couple of close calls. We had the snowball Earth, if you remember from Monday's lecture. We've also had some pretty big collisions in Earth history. And if those happen elsewhere in the solar system or in the universe, then it will be difficult for life to continue. So all of these things are really sort of necessary for life to exist. So let's have a look at each of these in turn. So in our solar system, we definitely have all of these elements. This means that we must have formed from maybe like a 3rd, 4th, or 5th generation nebula, so something where we'd had previous solar systems or previous stars that have exploded and left behind these different elements for us. And we assume also that habitable planets or habitable bodies are going to be terrestrial in nature. And that's because they have a surface, they have a sort of that crust where all of these elements can be concentrated. And they also have gravity similar to what we experience. Some of the gravity that you'd experience on Jupiter is just immense. And so it seems like it would be a friendlier place to be on a terrestrial body of some sort. Okay, sources of energy. So people have already named me one source of energy. What's one source of energy? The sun. Is all of life on Earth supported just by the sun? What else do we have that's actually independent of the sun? Sorry, someone? Anyone brave?
Radioactive material.
Radioactive material, and whereabouts is that usually?
We have to mine it.
We do, so yeah, so actually there are some sort of creatures that can live, and they instead of doing photosynthesis, they could do chemosynthesis. And they might live sort of pretty deep down in the earth and use chemical reactions. But I'm thinking of one particular place on Earth. Volcanoes. And whereabouts are those volcanoes? Under the sea. So have you heard of hydrothermal vents? These undersea volcanoes? No? Okay. Well, there's a video, and that's your task for today, is to watch that video. So we have these really cool, sort of, along those mid-ocean ridges, things like that, we have these underwater volcanoes, and at those we have this really hot water full of interesting chemicals coming out, and that geothermal energy, we call it, actually supports its own little ecosystem completely independent from the photosynthetic sort of processes going on at the surface. And they're really fascinating places. And it's one of the places which is theorized as a potential place that life could have started, is we're sort of cooking together all of these nice organic chemicals. Okay, so hydrothermal vents, black smokers, if you haven't seen them, please do watch the video. They're very cool. Okay, so let's talk a little bit more about our sort of energy source of the sun, because really that is the main driver. The vast majority of the energy that's used on Earth in the climate system, by the biosphere, other ways, comes from the sun. And so not only does nuclear fusion create those heavier elements that we need for life, but that sort of process where we take 4 hydrogen atoms and we fuse them together to form 1 helium atom actually releases a huge amount of energy. If you've heard of nuclear fusion as a potential saver for the Earth, because we want to be able to reproduce that process because it releases enormous amounts of energy. And unfortunately, we just haven't been able to do that yet. That sort of technology is slightly beyond us still. And the reason that this process releases energy is because if we add up the mass of 4 hydrogen atoms, it's slightly more than what is in 1 helium atom. And so where does that extra mass go? Do you remember this formula, E equals mc squared? Use it when you want to sound intelligent. Okay, well this is actually a real use of this. That leftover mass actually is converted into energy. And that is the energy that radiates out from the sun and reaches us at Earth and reaches out even further. Okay? And we'll talk a lot more about radiation from the sun on Friday, but as a quick introduction to it, that energy that's coming out from the sun is in a form that we call electromagnetic radiation. It travels as paired electric and magnetic waves, so that's why it's linked together. And it's the stuff that we're familiar with. We all hear about it. So radio waves, gamma waves, gamma rays, X-rays, visible light, ultraviolet light, things like that. Those are all different forms of electromagnetic radiation. It forms a spectrum. And it all travels at the speed of light, at 300,000 kilometers per second. And we use 2 different sort of ways of describing those waves. We can use wavelength, which is the distance between each crest. So each peak here, so the distance between here and here is 1 wavelength. And the closer those waves are together, the higher, or the shorter the wavelength, the higher the energy. Okay, so radio waves are really long wave. Okay, so they don't contain a lot of energy, they don't tend to be damaging for us. Things like ultraviolet have a much shorter wavelength, and so contain more energy and can be more damaging for us. We also describe things with frequency, which is related to that wavelength. But most of the stuff we'll refer to in the class will be to do with wavelengths. Okay. So this is the spectrum. So when we talk about ultraviolet and visible and gamma rays, things like that, it's all just a portion that we've arbitrarily defined on this sort of spectrum. Okay? So the sun doesn't just emit 1 wavelength and another wavelength and this wavelength. It emits the whole range. Okay? It emits most of it in the visible range, but actually it emits all different types. Okay? And we'll come back again to this on Friday. Okay. So I've definitely said electromagnetic energy from our star is important. And if we're going to develop life, an intelligent life, if we call ourselves intelligent life, and sort of have life around for a long time, that means that our star has to be stable and it has to be pretty long-lived. So does anyone know how much longer our star still has to go? 5 billion years. We're middle-aged, okay? We've had about 5 billion years of life, and we still have 5 billion years left to go. And how do we know this? By looking again at other stars in our galaxy. So you can see there's this really complicated looking diagram here, which isn't at all, I promise. So we have temperature across the bottom axis, increasing towards the left, and then we have luminosity, which is basically just how bright the star is, increasing up the y-axis. And you can see that most of the stars in our galaxy form along this sort of line going up through the center there, which is called the main sequence. And as our sun ages, as we start using up more hydrogen and sort of start burning more fuel, then actually our sun becomes brighter. You might think that it was brightest at the beginning and it's been getting fainter. It's actually the reverse. It was fainter in the past, and we're actually getting brighter and brighter and brighter through time. We're never going to go into a supernova. We're not big enough. Only really big stars do that. What we are going to end up, though, we're going to end up as a white dwarf. And people always ask me, when's the end of the world? And that was especially last year when it was 2012 and all the rest. 5 billion years' time, we've got plenty of time, don't worry about it. But at that time, the sun is going to be burning other fuels, and it's actually going to be expanding. And it's actually probably going to expand about to where Earth's orbit is right now. And at that point, all of the seas will have boiled off, will have melted the crust. It would not be a healthy place to be. Okay? So we're going to end our life as Earth in the sort of the outer bits of the sun. Okay. So, third thing related to the second is the presence of liquid water. So absolutely, we need to be the correct distance from the sun, someone was telling me down here. And not only that, but we need our orbit to be pretty regular, so circular enough that for part of the year we don't swing out way sort of far, and other times we stay close enough, okay? So suitable distance from the sun and a regular orbit is important. And this is what we call the habitable zone, so where it's not quite too cold and it's not quite too hot, and that's where the Earth is today. It's floating in the middle there, okay? But what else might affect the width of that habitable zone? So okay, distance from the sun helps, but what are we concerned about changing temperature on Earth today? CO2. So things like the composition of the atmosphere will also have a control on whether you're in the habitable zone or not. And in particular, when we look at Venus, Venus's atmosphere is 95% carbon dioxide. It has a huge greenhouse effect compared to Earth. And so even though it's just on the warm side of that habitable zone, in reality, it would be like standing in an oven if you were to stand in Venus, okay? So much more about this on Friday, okay? Not only do we need to be in the habitable zone to have the presence of water, but we also need volcanism in the first place. The volcanic gases released during sort of volcanic activity is what has created our atmosphere. So it's produced our sort of CO2 and gases in the atmosphere, as well as water vapor, which has gone into forming our hydrosphere. We need enough gravity to retain that atmosphere. And we also need our magnetic field to protect the atmosphere from solar wind. The other place where we have liquid water in the solar system is actually, we think, on the moons around the big gas giants. And so we'll have a look at these in a couple of seconds. But around those moons that are orbiting, they're way outside the habitable zone as we see it. But actually, the gravity that those moons feel as they move around Jupiter and Saturn stretches them, pulls them backwards and forwards, and generates energy. And that sort of geothermal internal energy is thought to allow sort of these salty seas to develop underneath the surface. It's very cool. Okay, and lastly, I've already talked about this, so I won't go on about that. So, lastly, I wanted to introduce this idea that life itself, once it developed on Earth, life itself has had a really important control on keeping us stable enough. And this is again something we'll talk about on Friday. But this is the idea of this Gaia hypothesis that the biosphere and the Earth itself acts as a system that sort of self-regulates. So if it gets too cold, for example, life might not grow, so plants might not take as much CO2 from the atmosphere, so CO2 might build up in the atmosphere, which might make us warmer again. So we have these little negative feedback loops that we talked about last week, and life often plays an important role in that. So could the biosphere itself not be acting to keep us at the right sort of temperatures for life to exist? Okay, so options within our solar system. So here are our 4 terrestrial planets. Mercury, no chance. Okay, it's really close to the sun, it's really hot. You can see it's really very small and it hasn't got the gravity to retain an atmosphere. So Mercury's out, we can rule one out. Okay. If we look at Venus, Venus is called Earth's evil twin because it's so similar in size to us, but it's just a little bit too close to the sun, and so it was warmer than the Earth, and that meant that life hasn't developed, it hasn't been able to remove that carbon dioxide from the atmosphere, and so today it's a really very hostile place. It doesn't necessarily rule out the potential that life could have existed earlier, but it's going to be really difficult for us to find signs of that. And so the only idea to do with Venus is a slightly crazy one about sort of organisms in the clouds around Venus. Then we have the Earth and our moon, and this little video here has a cool little animation about the moon formation if you'd like to find out more. And then we have Mars, which is where a lot of our energy is focused on, and that's because Mars is pretty small, and it's lost a lot of the heat, so the bigger you are, the slower you cool down as a planet. And so Mars is that bit smaller, it's sort of cooled down a lot more, so even though it had things like sort of volcanic activity in the past, it's sort of geologically dead now in that respect, and so we don't have new gases going into the atmosphere, and those gases have gradually been escaping out to space because it's a little bit smaller, and so its atmosphere now is so thin that it's difficult, not impossible for life to exist, but it's difficult. So I just sort of talked about Venus. The only potential place for life on Venus right now is in those clouds around that, and it doesn't seem terribly likely. Mars, though, Mars is fun. Do you know there's even someone with a job at NASA, and their job is to make sure that all of the stuff we send to Mars doesn't have any life from Earth on it. It has to be sterile, because we've found that things like lichen or lichen, whatever you call it, those really simple plants can grow pretty well in Martian conditions if it's sort of protected. So we have to make certain that we're not going to infect Mars with life from Earth, sort of the reverse of Martian invaders. We're invading Mars with our life, okay? And so this is sort of a really cool place to look at right now because we have these rovers. We're finding clear evidence that there was liquid water on Mars in the past. We probably had sort of seas for quite a while. There was this thick atmosphere. So it had really similar conditions to what we had on Earth as life was developing. And if we can find life on Mars, then there's a really good bet that we would be able to find life, or at least the odds of life existing elsewhere in the universe really get a lot better. Okay, Europa. This is a really interesting one. Okay, so Europa is a moon around Jupiter. And you can see on the surface there, it's actually an ice surface, but you can see those cracks. And we think that those cracks are there because there's liquid water underneath, because there's geothermal energy and potentially geothermal vents and things like that underneath. So there could be life underneath there. It's protected, it's not in the classic habitable zone, but it's potentially there. The same is true for Enceladus, or I think it's Enceladus. I can always get those mixed up. But this is a moon around Saturn, and it's again the same sort of thing. You can see there's an icy surface, but you can see marks where it might be pulling apart. And in fact, one of the probes that NASA launched flew through these little plumes where geysers were erupting material out to space. And what they could detect was that there must be warm, salty material underneath that ice. And they could detect carbon and oxygen and things that we would need. So that's a really interesting place we could look as well. And lastly, for one that's really far out there, we have Titan. So Titan is another moon of Saturn, and it doesn't have that ice covering that the others do. Instead, it has lakes of hydrocarbons. So it's a much colder environment. And instead, if we could sort of substitute hydrocarbons for water in the reactions that we're interested in, who knows? But as I said, it's a little bit far out there. So if you could go to one of those, where would you go? Mars, Europa, Enceladus or Titan? Okay, and I have 2 more minutes, and then I'll let you go, okay? So let's see what people said. So most people want to continue exploring Mars. I think it's our best bet for now, I would agree. 2 more minutes, and then I'll let you go, I promise. Okay. So I wanted to remind people that we don't just have planets around in our solar system. We have the Kepler telescope, which has even been updating us since your book has been in existence. And we now have these planets which are really similar to Earth. And we can detect smaller and smaller ones. So Earth is up there on the right-hand side. And if we use a similarity index, so Earth is 1, the closest planet has a similarity index of 0.92. It's really similar. For comparison, Mars is 0.66. Okay? So it's not just within the solar system, but outside as well. I'll ask the remaining question on Friday. Okay, thank you.